Hello dear students, glad to meet you again in this last session. In this session 2.14 from chapter 2 structure of atom in grade 11, we are going to discuss about the symmetrical distribution of electron and exchange energy. Before getting into today's concept, let us recall all the topics that we have discussed in the previous sessions. In session 1, we have discussed the discovery of subatomic particles. In session 2.2, we have discussed J.J. Thomson and Rutherford atomic model and its drawbacks. In session 2.3, we have discussed dual nature of electromagnetic radiation. In session 2.4, we have discussed atomic spectra. In 2.5, we have discussed Bohr's atomic model. In session 2.6, we have seen two developments towards quantum mechanical model of atom. 2.7, we have discussed quantum mechanical model of atom. In session 2.8, we have discussed orbital and quantum numbers. 2.9, we have discussed shapes of orbitals. In session 2.10, we have discussed energies of orbitals. In session 2.11, we have discussed filling up of orbital. In session 2.12, we have discussed the electronic configuration of first 20 atoms. In session 2.13, we have discussed the electronic configuration of atoms with atomic number from 21 to 30 and the exceptional configuration of chromium and copper. Learning outcomes. Students, at the end of this session, you will be able to elucidate symmetrical distribution of electrons, explain the stability of completely filled and half-filled orbitals, and expound exchange energy. Now let us see the symmetrical distribution of electrons. Symmetrical means similar or identical. In Tamil, we will call it as samachir, right? Seerana, ore madriyana, right? The completely filled or half-filled subshells have symmetrical distribution of electrons in them. If you look at the degenerate p orbital, the completely filled or half-filled subshells have symmetrical distribution of electrons in them. If you look at the degenerated p orbital and d orbital here, you could see the symmetrical distribution of electrons, right? If they have the symmetrical distribution of electrons in them, then they have a greater stability. For example, if you take the degenerated p orbitals such as px, py, and pz, these double shape orbitals or p orbitals, right? What is the meaning of degenerate orbital? Degenerate orbitals means they have equal energy, but the only difference is the orientation, right? Here the px orbital in the x direction, py orbital in the y direction, and pz orbital in the z direction, right? And due to the symmetrical distribution, the shielding of one another is relatively small and the electrons are more strongly attracted by the nucleus. Shielding means preventing or screening, enclosing, right? In Tamil, we'll call it as kavasam, right? The shielding of one another, the shielding of x orbital and y orbital, or x orbital or z orbital, or y orbital or z orbital. The shielding of one another is relatively small and the electrons are more strongly attracted by the nucleus. So it increases the stability. Let us understand this concept by taking chromium as an example. Stability of half-filled and completely filled orbital in chromium. If you look at the expected configuration of chromium, we have 4s2 and 3d4. When you see the orbital configuration of chromium in the expected configuration, we have 2 electrons in 4s orbital and 4 electrons in 3d orbital, right? If you notice the 3d orbitals, the electrons in them are not symmetrically distributed. We know that d orbitals can accommodate a maximum of 10 electrons. Here we have only 4 electrons. It is neither completely filled nor half filled, right? At the same time, if you look at the actual configuration of chromium, we have 1 electron in 4s orbital and 5 electrons in 3d orbital. In this case, 1 electron from the 4s orbital has shifted to the 3d orbital. If you look at the actual configuration of chromium in the orbital diagram, that is the 4s orbital and the 3d orbitals, all these orbitals are half filled and the electrons are symmetrically distributed and have the same spin. So this actual configuration of chromium is more stable when compared to the expected configuration of chromium. That's why chromium has an exceptional electronic configuration. Now let us see copper also. When you look at the orbital diagram for copper, we could see up to 4s it is completely filled. Coming to 3d orbitals, it is not completely filled or it is not half filled, right? How many electrons it has? 9 electrons. In the last orbit, it has only 1 electron with parallel spin, right? It is partially filled. At the same time, when you look at the actual configuration of copper, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 and 3d 10. In this case, 1 electron from 4s orbital shifts to the 3d orbital, so that here the 3d orbitals are completely filled, right? Moreover, the maximum number of electrons that can accommodate by s orbital is 2, right? When it shifts 1 electron to 3d orbital, the 4s orbital becomes half filled and the 3d orbitals will become completely filled. So the 4s orbital is half filled and 3d orbitals are completely filled. So it attains more stability when it compares to the expected configuration. Now let us see the next concept, exchange energy. The stabilization effect arises whenever 2 or more electrons with the same spin are present in a degenerate orbitals of a subshell. If 2 or more electrons with the same spin, if you see the orbital diagram of degenerate d orbital and p orbital, the electrons present in d orbital and p orbital here have same spin, right? That's why we have represented it by drawing an upward arrow mark in all these suborbitals. If 2 or more electrons with the same spin are present in a degenerate orbital, there is a possibility for exchanging their position. You have to note this point, exchanging their position. They are not pairing up, they are exchanging the position. For example, if the electron in the px orbital moves to py orbital, then the electron in the py orbital moves its position to px orbital. Only exchanging takes place here. They are not pairing up. If they have the same spin, then there is a possibility for changing their position. And during the exchange process, the energy is released, and the released energy is called exchange energy. If the exchange energy is more, then the stability is more. If more number of exchanges are possible, more exchange energy is released. More number of exchange energies are possible only in the case of half-filled and fully filled configurations. Let us understand this concept by taking chromium as an example. Now let us see the possible exchanges in the expected D4 configuration. So the expected configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d4. How many electrons are there in 3d orbital? 4, right? So we have to draw 4 upward arrow mark in the 3d orbital. Now let us see the possible exchanges in this d orbital. This diagram shows us the possible exchanges between first electron and the second electron, first electron and the third electron, first electron and the fourth electron. This first electron could not move to the fifth place because there is no electron. So no exchange could be done, right? So totally how many possible exchanges? Here we could see 1, that is 1 to 4, second 1 to 3, and third 1 to 2, right? So how many possible exchanges we could see here? 1, 2, 3 possible exchanges we could see here. Coming to this diagram shows us the possible exchanges between the second electron with third electron and second electron with fourth electron. Note that this shows the exchange between the second and the third, not from the first, right? Here you could see the arrow mark starts from the second place to the third place and the second place to the fourth place. So totally how many changes we could see here? 2, right? With the electron in the second place exchange with the fifth place, it cannot exchange because there is no electron in the fifth place, right? So totally how many possible exchanges we could see in this diagram? 1 and 2. Now coming to the third diagram, we could see the exchange between third and the fourth. Exchanges between third and fifth could not take place because there is no electron. The fifth place is empty over here. So how many possible exchanges could take place here? 1, right? Totally how many possible exchanges could take place? 1, 2, 3. 3 plus here 2. So 3 plus 2, 5. Then 5 plus how many? 1, right? So totally 6 possible exchanges we could see in this orbital. So total possible number of exchange energy is equal to 6 in the case of the expected D4 configuration. At the same time, now let us see the possible exchanges in the actual D5 configuration of chromium. The actual D5 configuration of chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 and 3d5. How many electrons are there in 3D orbitals now? 5, right? Now let us see the possible exchanges in the D5 configuration. This diagram shows us the exchange between the electrons in the first place to the second place, first place to the third place, first place to the fourth place, and first place to the fifth place. You could see all the arrow mark initially starts from the first place, right? So how many possible exchanges are here? 1, 2, 3, and 4, right? Coming to this diagram shows us the exchange between the second electron to the third electron, second electron to the fourth electron, and second electron to the fifth electron. So how many possible changes are here? 2 to 5, 1, 2 to 4, 2, 2 to 3, 3. So 3 possible exchanges are here. Now coming to this diagram shows us the exchange between the electron in the third place, right? Third place to the fourth place and third place to the fifth place. Note this diagram, this arrow mark begins with the electron in the third place. So how many possible exchanges we could see here? 2, right? Now coming to the last one, we have 1 electron in the fifth place in D5 configuration, right? So there is a possibility of exchange between fourth place and the fifth place. So how many possible exchange here? We could see 1 possible exchange. Since we have 1 electron in the fifth place, the possible exchange between the fifth electron with the other 4 electrons is possible in this D5 configuration, right? Now shall we calculate the total possible number of exchanges in the actual D5 configuration of chromium? Here we could see 4 possible exchanges, 4, plus here we could see 3 possible exchanges, so 4 plus 3, 7. Here we could see 2 possible exchanges, so 7 plus 2, 9. Here you could see 1 possible exchange, so 9 plus 1, totally we have 10 possible exchange energy here in actual D5 configuration. When you compare the possible exchanges in chromium in D4 configuration, that is the expected configuration, and the D5 configuration, that is the actual configuration of chromium, the exchange energy in the expected configuration, that is the D4 configuration, is 6, and the exchange energy in the D5 configuration, that is the actual configuration, is 10. In D5 configuration, the 3D orbital is half filled. Hence, exchange energy for half filled configuration is more. This increases the stability of the half filled 3D orbitals. It is very clear that the D5 configuration has more number of exchange energy. On the other hand, in the D4 configuration, that is in the expected configuration, only 6 changes are possible. This shows that D5 configuration is more stable when compared to D4 configuration. Therefore, D5 configuration of chromium is more stable. Students, let's recall all the topics that we have discussed in this last session. In this session, we have discussed the symmetrical distribution of electrons, stability of completely filled and half-filled orbital, and exchange energy. Hope this session was very useful to you. Students, so far we have discussed 14 sessions for this second chapter, Structure of Atom in grade 11. We have covered both Tamil Nadu syllabus, TN, SCERT and NCERT syllabus in all these 14 sessions. Hope all these 14 sessions are very useful to you. For your convenience, I have given all the 14 sessions video link in the description box. For better understanding, don't forget to watch all the 14 links. See you soon in the next chapter. Have a nice day. Thank you.